Okay, so welcome back to another video. So here today we have both a combination of a sum and integral, and we have the infinite sum of an alternating series from -1 to the power n plus 1 multiplied with the improper integral of the square root of x to the power 2n subtract 3 multiplied by the inverse tangent of x to the power 2n minus 1, all this being divided by 1 plus x to the power 2n minus 1 dx. So strangely enough, there's really no need to make things a little overwhelming yourself, because simply if we actually do a little bit of some substitutions, you're going to see this a lot in this video, especially that's pretty much the technique we're going to do in order to calculate this. Then it also follows with a couple results that two results that I've actually proven in past videos that I'll get to that. Well, really, I'll actually state that in the beginning before we actually solve like the entire problem itself. And relying on those results will actually make this entire, combination of both the sum and the integral easy to compute. So we'll actually just jump right in. I don't really have anything else to add because it's essentially mainly substitutions and just it follows directly from those, computations. So let's actually just jump right in. So let's start off by, I'm going to state the two results. And of course, I'm going to call this entire our given capital A. But anyway, starting from the results we're going to use, the first one I want to use is the inverse tangent of x. Add this with the inverse tangent of 1 over x is actually just going to equal pi over 2. So I did this little proof on one of the golden ratio integrals that I did. This is just a little side proof I did that I wanted to, get that across. So if you want to find that proof, I'll link that in the description below and that timestamp as well. And then the second I want to use is this following infinite sum. So we have that our index starts at 1 to infinity of the alternating. So -1 to the power n plus 1 divided by 2n minus 1. If we were to expand this out, we have 1 subtract 1 over 3, add this with 1 over 5, subtract 1 over 7, so on and so forth. That's actually going to equal pi over 4. Interestingly, this is actually Leibniz's formula for pi, and I did prove this in a separate video itself. Although the summation was not listed in this video itself, but the expansion was, and I did a little bit of a different approach compared to how we actually take it off from here. But if you want to check that out, the proof of that is in the description below. But that was also a fun video that I actually did, and a really interesting take on it too. So with these two results, let's actually now do the following computations. So now suppose, as I said, this is actually going to start with A. So let's actually first perform a little substitution. I'll call this T. And we'll actually substitute this for x to the power 2n minus 1. Now, if we were to solve this itself for x on its own, then interestingly, we have that x is equal to t to the power 1 divided by 2 subtract 2n minus 1. Then if we actually perform the differentiation, then we see that dx is going to equal, so everything here is just using the power rule. So this is just 1 divided by 2n minus 1 multiplied by t to the power 1 divided by 2n minus 1, then subtract with 1. So minus 1, then minus 1, then followed by dt. So now from here, now let's actually, put in that entire substitution. And we're going to focus on, of course, this integral first, then proper integral. So let's start off with this integral over here. So this is from 0 to infinity of, now I'm just writing the what we were given. So minus 3, then inverse tangent of x to the power 2n minus 1, all this being divided by 1 plus x to the power 2n minus 1 dt. Now we actually performed the correct substitution. Simply, the bounds are actually going to remain the same, go figure. So 0 to infinity, then we're going to have the new, so let's see, we plug in for x over here. So inside the radical, the square root, we're actually going to have t then to the power 2n minus 3, all this being divided by 2n minus 1. Okay, so that's the radical expression inside. So the inverse tangent, then this will just be t, all this being divided by 1 plus t, then follow with the substitution, our dx substitution. We just plug in, so 1 divided by 2n minus 1, then t to the power 1 divided by 2n minus 1, then minus 1, then dt, just like that. Okay, then simply we can actually do a little bit of simplifying. We can actually put the 2n minus 1 outside of our integral. So we have 1 divided by 2n minus 1, then our integral over here. Then we can actually rewrite the, the square root as the exponent 1/2 and then, fill in the gaps with the, the exponent. And same thing for over here, they share the same base over here, so I'm actually going to combine that together as well. So simply now we would have t to the power 2n minus 3, then 2 times, that's coming from the 1/2 of the square root, 2n minus 1 over here. Then we just add this with the 1 divided by 2n minus 1 subtract 1, then just plug in the inverse tangent, so place that back in t, then we just divide this over here by 1 plus t and dt, just like that. Now, this part's actually do a little bit of a simplification. So if we actually notice something, this is actually going to be a quick computation over here. So we see that 2n minus 3, then divided by 2 times 2n minus 1, then add this with 1, 2n minus 1, then minus 1. Simply, if we actually just do a little bit of getting the common denominator and all that, then the expression is follows. So 2n subtract 3, then I just multiply the 2 on the top, so we add this with 2. Then over here can be written 2 times 2n minus 1. So then this will be minus 2, then 2n minus 1. All this being divided by 2 times 2n minus 1 on the bottom. Then we simplify this out. So let's see, 2n minus 4n, so it's negative 2n, minus 3 plus 2 is negative 1, minus minus, so plus 2, so then we will get a positive 1. I'll rearrange the terms, so I'll have 1 minus 2n, then divided by 2 times 2n minus 1. Get a common denominator, they share the same terms. If I just factor out the negative 1, so those two terms will cancel, and so we're just left with negative 1/2 from that, the base t over here. We're gonna have our new rewritten integral, or more simplified rather. So we have 1 divided by 2n minus 1. Then we have the integral from 0 to infinity. This will be t to the negative 1/2, then inverse tangent of t, all this being divided by 1 plus t dt. Now from here, we can actually just put this back into our, with the infinite sum over here. So let's actually move on from that. So now plugging this back in, again, I called this capital A. So now capital A is going to be the following. So we have the infinite sum, n is equal to 1. So we have this alternating series, but then we just replace everything from over here with the new substitution from this integral we just calculated, or rather, I guess, simplifies the more technical term to say this because we haven't really computed anything. So now we would have negative 1 to the power 2n, or rather, this is n plus 1. n plus 1, all this being divided by 2n subtract 1. Now we just, same integral again, so 0 to infinity of t to the power negative 1/2, then inverse tangent of t, all this being divided by 1 plus t dt, but using the result that we have shown, that we say that this infinite series over here is equal to pi over 4, so this can be replaced. So now we have pi over 4, and then now multiply with the our improper integral, so nothing's changed from that integral itself that we just substituted. Inverse tangent t, then divided by 1 plus t, then dt. Now comes calculating this integral, so let's actually do that. So a little trick we're going to actually do a little bit something clever is we're actually going to break the bounds of our interval of our integrand. So if we're starting off with our given, then I actually want to start with our bounds starting with from 0 to 1, and then add this with the remaining rest of the interval going from 1 to infinity. So give me a second to actually write all that out. So now we have this, we broke the sums up from the intervals itself, adjacent intervals, another way to put this. So I'm actually going to calculate this integral over here. So we're going to do another substitution, and we're actually going to call this variable s. So now first I'll let s, this is blending in, so let me change a different marker. We're going to let s equals 1 over t, and if we just solve for t on its own, that basically says that t is equal to 1 over s. Do the differentiation and say that dt is basically just equal to negative 1 divided by s squared ds. All right, and from here, this is the substitution we're performing just to imply that. So now we would have, so I'm actually going to rewrite this integral again. So let's see, 0, 1, t negative 1/2 inverse tangent of t divided by 1 plus t, then dt. And now we're going to add this with our new substitution over here. So let's see, if I calculate the new bounds, our upper bound for here in the world of S is going to be 0, since for infinity, if we plug this back here, then it's going to approach 0. And plug 1, so that'll be 1 over here. Then we plug S, plug t. So on the numerator, we're going to have the square root of S, and then multiplied by the inverse tangent of 1 over S. This is being divided by 1 plus 1 over S, and then multiplied with the substitution, our differential s squared ds. Then we can actually do a little bit of simplification from over here. So I think it's best to justify now, say that over here, we can write this as a new simplification and say that over here, this is going to be now, if we just distribute the s squared, so it's s squared plus s, factor out the s, and you can simplify with the square root of s, and then flip the bounds because we have an upper bound and a lower bound, not working 0 as the upper bound, 1 as the upper bound, negative, the negatives cancel. So actually doing all that simplification over here. So we write a plus just to denote this from here. So this is 0, 1. On the top, so we're going to get a s to the power negative 1/2, and then all this divided by 1 plus s. And then we have a tangent of, inverse tangent of 1 over s. We can actually use the result from over here. All you gotta do is just subtract subtract the inverse tangent of x to both sides. And so replace this, now we have is just pi square, then subtract inverse tangent. Now, of course, in this situation, we're dealing with the world of s, then ds. Then if we actually just do a little bit of distribution, so what you'll notice is that anything associated with the inverse tangent s is actually going to cancel out. So that actually just means that simplifying, so let me put it like this. If I just cross out, so this crosses out by itself. Then if I distribute the inverse tangent, so this will cross out by its own. These two terms are going to cancel each other out after that entire distribution. I know that we have variables t and s, but variables don't really matter in this situation. So as long as you're integrating in respect to the variable and these integral matches, especially with the interval itself, then it's good to go. So really, we're only left to just evaluate after distributing the pi over 2 to this integrand over here. So last but not least is just pi square, or pi over 2, then multiply with the integral from 0 to 1 of s to the power negative 1/2, then 1 plus s ds. And so if I want to write this just a little bit simplification, I can actually put the s to the negative 1/2 on the bottom. So really it's just pi 2, then 0, 1, then 1 divided by the square root of s, then multiplied by 1 plus s ds. Now we're actually going to do one more substitution, and I'm going to let s equals tangent squared theta. Then if I do the differentiation, so ds is just going to equal 2 times. So this is actually just apply the chain rule. So this is 2 times tangent theta. Then take the derivative of the inside, which is tangent theta, which is going to be secant square theta. Then from here, if we actually just perform the substitution, so pi over 2, then so now our new bounds in this situation, so if we plug 1 for s, theta is going to be pi over 4. And then if we plug 0, it's just going to be 0 on the bottom. So over here we have 2 tangent theta, then there's supposed to be d theta over here. Then multiply with secant square theta. All this being divided by, if we just plug the square root of tangent theta down below, then multiply with 1 plus tangent squared theta d theta. We see that this trig identity 1 plus tangent squared theta is actually going to be secant squared theta. Guess what? That cancels that out. And then tangent of squared theta is just tangent theta. That cancels out. So really, all that's left is just pi squared multiplied with 0 to pi over 4 of 2 d theta. And if you actually perform all this calculation now, this is actually just simply, you can see that we're going to get that this is just pi squared divided by 4. But we're almost done. We have shown that this entire integral, I'll put this way. we've shown that this, this value over here, pi squared over 4, is actually just going to equal this integral, this improper integral over here. So all that's left now is that a is equal to, we set this as pi over 4, then multiply with this improper integral we calculated, which is just pi squared divided by 4. And finally, the final answer comes down to just pi cubed divided by 16. And just like that, we are done with the computation. Just like that, a combination of sums and a combination of a sum and an improper integral leads to this beautiful result, just like that. So yeah, that's pretty cool if you ask me.